Hi everyone, welcome back to AP Environmental Science. In today's video, we're going to be covering topics 6.6 and 6.7. So let's go ahead and get started. This is like the fourth time I've tried to record this, so I'm sorry if I sound a little annoyed. Okay, let's go ahead and get started. So, and I gotta make my face small and over here. All right, so we're going to be talking about ocean warming and ocean acidification today. So we should know by now what the greenhouse effect is and currently how our global temperatures are slightly increasing. So due to burning fossil fuels, car emissions, cities, pollutants, we are currently raising our atmospheric temperatures because we are currently releasing greenhouse gases into the atmosphere. Greenhouse gases include things like carbon dioxide, nitrous oxides, methane, so on and so forth. So what they do is they trap heat in our atmosphere because it prevents the heat and light energy from escaping back into space. So because we have an increase of atmospheric temperature, we're also going to have an increase in the ocean temperature as well. Heat is transferred to the ocean. Think of it kind of like, boiling a pot of water on a stove. The more heat that you add to the pot, the faster the water is going to boil. So ocean absorbs heat radiated back to Earth by greenhouse gases. And we have a, general warming trend around the world. In certain parts, the ocean is cooling slightly, but the majority we can see here in this image, the majority of the ocean is warming, particularly along the east coast right here, as well as on the eastern coast of Asia and Japan. So oceans absorb much of Earth's heat due to high specific heat of water. 90% of Earth's warming has come in the past 50 years has occurred in the oceans. Okay. So the thermohaline circulation distributes heat absorbed at the surface, the depths, and other areas of Earth. So this is the concept of density here, where hot water is going to be less dense than cold water. So hot water will float, whereas cold water will sink. So the heating of the oceans is messing up how the water circulates within oceans. And that is going to disturb how nutrients are going to be distributed throughout the ocean. Heat absorbed by ocean can transfer back into the atmosphere for decades. So if you have hot atmosphere, hot ocean, hot ocean, hot atmosphere, they have this like positive relationship between the two. So how does this affect marine species? Warmer water holds less oxygen, causing respirative stress or suffocation. So remember, low oxygen concentrations in the water is hypoxia. The migratory routes and mating seasons can be altered, especially for whales. The reproductive timing is typically tied to temperature and can be disrupted. So in humans, for those of you that do not know, a menstrual period is, started by a release of hormones. We have hormones controlling our mating season, per se, the release of our eggs. Whereas in other species, they do have hormones that control it, but those hormones can be triggered by changes in temperature, okay? Certain temperature ranges even can determine the sex development of different species, like certain frogs. So when you change the temperature of the water, you can potentially be affecting the population, not because they would die from ecological tolerance issues, but because their population might not recover from not being able to reproduce properly, or only kind of causing one type of sex to develop within a population. When you have the oceans warming, they can also cause habitat loss. And one of these things that is, we are losing at very fast rates are our coral reefs. So coral bleaching is going to occur with the heating ocean. You have these shallow, sunny waters, ideal for algae and coral, become deeper from the ice melting. So as the ice caps and land-locked ice in particular are heating and melting and entering the ocean, it's creating sea level rise. So when you have this sea level rise, your shallower waters are going to become deeper, meaning that light is not going to penetrate as far, and that can alter the productivity. Productivity is the rate of photosynthesis, and the number one thing you absolutely need for photosynthesis is sunlight. Toxic algal blooms. Toxic blue-green algae prefer warmer waters and warm temperatures. It prevents the mixing of water. The warm temperatures prevent the mixing of the water, enabling these algal blooms, which are bad because we know a really thick algal bloom will cause the light to not penetrate. So those organisms underneath the algal bloom are going to die. Also, plants do perform cellular respiration. They're going to be absorbing all the oxygen in the water, leaving very hypoxic conditions for the organisms that only do cellular respiration, like the other fish. So this is just essentially an overview of how climate change and global warming is impacting coral reefs in particular. And this is something that you should have gone over or learned a little bit more about in the gizmo. Okay, coral bleaching. Coral reefs are this incredibly biodiverse and highly productive aquatic ecosystem. They have this mutualistic relationship between coral and photosynthetic algae. So remember, mutualistic means both species are benefiting or getting something out of that's positive in this relationship. The algae supply sugar, which is food, and the coral supply carbon dioxide and, detritus, which is going to be nutrient containing organic matter, kind of like waste. The algae have a very narrow temperature tolerance. Remember, all living things on Earth have a range of tolerance that can be temperature, pH, salinity, even exposure to light. They have this range of tolerance that they can survive and thrive in. When you're outside of that range, the organism can start to experience stress, which affects how well they are able to survive and reproduce. Too far out of that range, they're going to unfortunately not be able to survive. So algae have this very small, narrow range of temperature tolerance. So when you're outside of that range, you're too high of a temperature, the algae are going to die. Now the algae are no longer supplying a food source for the corals, and without food, the corals are unfortunately also not going to survive. Pollutants from runoff, which can be things like sediment, pesticides, sunscreen, which we'll talk about in our pollution unit, can also force the algae away from the reef. The coral lose color and become stressed and vulnerable to disease without algae because, again, algae is their main source of food. Okay, now let's talk about ocean acidification, which is exactly what it sounds like. And you guys should be familiar with this because we did our ocean acidification lab. All right, so when you have an increased concentration of carbon dioxide in the atmosphere due to the burning of fossil fuels, you're also going to have an increased amount of carbon dioxide in our oceans. It's this direct exchange. The oceans absorb carbon dioxide for a variety of reasons. A lot of photosynthetic organisms living in the ocean, and I shouldn't say, all of them are going to be using CO2 to perform photosynthesis. So CO2, some of it is going to combine with the ocean water to form carbonic acid. And acids are lower on the pH scale. Acids have a 1 to a 6 range. 7 is neutral, 8 to 14 is basic. So when you have atmospheric carbon, atmospheric CO2 increasing, it's going to increase the oceanic carbon as well. It's going to mix with the water and form carbonic acid. So the carbonic acid dissociates into a bicarbonate ion and a hydrogen ion. Hydrogen ions are what make things acidic, okay? So the carbonic acid is going to dissociate or break into different things. One of them is going to be the bicarbonate, one of them is the hydrogen. So essentially, see how it's H2CO3? H2 means that there are 2 hydrogen atoms. C means that there's 1. O3 means that there's 3 oxygen atoms all bonded together. So this carbonic acid is going to dissociate. It's going to break. And what exactly is breaking off? 1 hydrogen ion. And this hydrogen ion does not like being by itself. It's going to combine with a carbonate ion, and they're going to make more bicarbonate ions, okay, here and here. So it's kind of like the whole, oh my gosh, my brain, the stratospheric ozone depletion that we talked about way earlier this year. Similar, but different. Okay, so why is this an issue? The more hydrogen ions you have, the lower the acidity. Remember, the stronger the acidity, the lower the pH. So more hydrogen ions, the more highly concentrated of hydrogen ions, the stronger the acid, the lower the pH. So what impacts does this have on shelled organisms? The marine organisms that make shells use calcium and carbonate ions to build their calcium carbonate shells. So if you have those free hydrogen ions binding with the carbonate ions in the water, the shelled organisms cannot make their shells because the carbonate ions are bonding with the free hydrogens and forming the hydrogen bicarbonates, okay? So as the CO2 increases and the ocean acidification makes the carbon ions less available. Can I move my head? Yeah. So carbonic acid increases the amount of the hydrogen ions which bond with the carbonate to form bicarbonate. Marine shells break down as pH decreases and carbonate ions are less soluble in ocean water. Fewer carbonate ions, less calcification, weaker shells of different corals, mollusks, and urchins. Oh, I keep moving myself in the wrong spot. There we go. So this is, what we did in our ocean acidification lab. These shells are going to break down over time, especially in exposure to higher concentrations of strong acids. So some anthropogenic causes for ocean acidification: fossil fuel combustion, deforestation, coal gas combustion, all of that lovely stuff. So this is stuff that we should know by now. The carbon dioxide is directly associated with ocean acidification. That's an inverse relationship between atmospheric CO2 and ocean pH. So inverse is as one goes up, the other goes down. And remember, a decrease in pH means more acidic, okay? A decrease in pH means more acidic. So as we can see here, as atmospheric CO2 increases, the acidity of the water is going to decrease, the pH of the water is going to decrease. The ocean pH has decreased from 8.2 to 8.1 in the past 150 years. It could decrease to 7.8 by 2100. That's just weird to say. Now, again, that might not seem like a lot, an 8.2 to an 8.1, but you have to remember that the pH scale is on a logarithmic scale, So what does that mean? I don't know if I have it large enough here. Here we go. So a logarithmic scale means it goes up by tens between each step. So a pH of a 0 is technically going to be 10 million times stronger than a pH of a 7. Okay? So even though it's a difference between a 0 to a 7, it's 10 million times stronger. So even going down from an 8.2 to an 8.1, that's a significant amount. Because remember, life on Earth has this range of tolerance, and if these species have a very narrow range of tolerance, it's going to disrupt their ability to survive and reproduce. Yep, 30% decrease. I have it right there. So that's significant, pretty significant. All right, that is all I have for you guys today. This unit is now wrapping up. Please make sure that you have turned in all of your work so far for this unit. The grade book should be up to date by the time you are watching this. If you have anything missing and in the grade book, but you did turn it in, make sure you email me as soon as possible. I have this gigantic pile of all of your work. I will just go through it, or you can go through it and show me, hey, I did turn this in. It is a lot for me to go through. If you have something missing and you did not turn it in, please get it to me as soon as possible. Okay. If you have any questions, let me know. I will see you guys all soon. Bye.